We are at the 15 kilovolt, right? You keep looking at this. Now we lower it down to 10, to 5. No alignment. Just one scan, they come back, right? You will see. We will lower down again. Now we go to 1 kilovolt, 15 times smaller already. It's still very clear, but as you can see now, the surface detail becomes slightly clearer, right? Because low volt. Yes. Now we're going a bit down, 500 volt, right? 500 volts. Now you see the surface, the wrinkles and all that is yeah. But of course, with the lower voltage, we lose a bit of electrons, right? So it looks a bit dark, but now it's 200. It's still very clear, right? It's still very clear. And we will push this system to the limit, 24. And what we did after every changes is only to change the contrast and brightness, that's all. Alright? It's a bit dark, but when the contrast and brightness adjusted, yeah, you can really see the surface. So depend on, it's the same sample, depend on what you want, right? Nowadays we publish a lot of papers and the question, oh, can you show me the surface details? How do we get it? This method. Alright? I hope this video, these two videos as an introduction is really capture your attention, how powerful the machine is. So I will go through these materials, parameters, right? So there are many parameters. So the first time FESEM you say your hand is shaking. So many parameters, how do I control? What is this thing do? What is that thing do? So I hope by the source and all these are the shortkey type, because we have a conventional SEM where you use a metals like a tungsten or lanthanum hexaborate LAD6 or CE cerium oxide to an electron will be extracted and we will focus the electron to the samples, right? Right. The reason that we can see the surface clearly on the low surface is you can have a small aperture, large aperture, and all these have different. If you want a good, is controlling the focus now. Blur one way, he go the other way. Okay, now it's much better. No, yeah, he's still going the other way now. Okay, now he's doing astigmatism. You can see that it's become clearer. This is the Y astigmatism. And you do X1. Yeah. You see. Right, just by controlling certain parameters. A lot of students always come to me that I cannot take a good image, it's so bad, is my sample bad? No, it's just you don't know how to use the microscope properly. When you know how to do properly, actually, you can extract the, right, because once you have good samples, half of the battle is done. A lot of students, when they come to the microscope, they just hastily try to paste the things and use their fingers and all those things. And when they put into the microscope, oh dear, I cannot see anything. Or I see a lot of contamination, right? So please spend a lot of time to go through the sample preparations, all right? Really important. And I hope in the afternoon, when we do the demo, hands-on and so on, I can discuss with you what kind of sample you're working with and what is the best practices. But I will not use this deck of sweat. I have a better one to show you how the sample preparation is being done. Right? Bulk sample, powder samples, cross-section samples, and so on and so forth. So we will discuss. Normally, if you buy a microscope, I hope my Indian colleague here supply you with all these, the carbon tapes, the pads, the carbon pen, the silver pen, and all that. These are the tools that you use to mount your samples. Okay? But remember, all these are not your sample. Right? When you introduce it to the sample order, you introduce the sample, there will be some sort of, you must know your sample tree. These are not your sample. So the idea, for example, use as little as possible. That's the bottom line. Right? Use as little as possible. Yeah, we don't recommend a carbon tap or carbon pads because they will give out a lot of carbon. When you do your EBX, you will know that there's a lot of information coming out that was not your sample. If you know, it's good. If you don't know, then you run the paper and say, oh, I saw a lot, then it's totally wrong, right? Yes. I'm an active reviewer myself, so when I see all this description, I know they are not expert in that. So they anyhow write, anyhow analyze the data. Trick to apply: if you use a silver and carbon paste, do not put a lot, do not smudge things. Put in two corners, one drop each, and place your sample there. Let it dry, blow dry it, and that's all. Okay? So we don't need to, like Leonardo da Vinci, you take the thing, no need. Just a two corner, that's it. Alright? Samples. We are looking at nanometers, right? Do you need such a big sample? No. Because if this sample is non-conductive, it's charging sample, all the electron build up will be there. You cannot see anything. What I need is probably just a small little corner of samples we put in, and there's much more. We are looking at nanometers, 10 to the power of minus 9. 1 millimeter we can cut into 1 million times. That's what we are looking at. So we don't need a big sample. Alright? So we mount the small amount in that corner, in the sample itself. Right? Cross section. A lot of people, they put the cross section, they just put place it on top. This is very bad because this is the pointy tube that all the electron will go in, right? Right? Because it's nearer to the column. So the charging will be all on the surface. Right? Never do this. We prefer generally a flat surface. Okay, I later will show you what is the effect of this thing. But normally we have this special holder, or if you are creative enough, actually you can just buy a piece of. Sorry, I should not say in front of my senior colleague because they will not buy consumable from you guys. But you can just get a steel bar or something that you cut in half and you can paste it sideways, right? But of course you can buy from them too. They have a lot of good stuff there.
You should buy one.
No, after this they don't give me dinner, so I need to manage the expectation.
You can share all your secrets later on.
Yeah. Yeah, this is my method, my favorite method for nanoparticles, for powders, right? When I start doing FESEM, nobody told me that I just sprinkle a lot of powder, but I want to see a single nanoparticle. You do this, you won't be able to see, and you will see just a lump of things, right? So I paste. This is a silicon wafer. You can buy a big one from online platform and just cut it with a small piece. You sprinkle some powders. Right? I prepare two tubes, then I just do it. Then a lot of people will argue with me, hey, I don't see any samples. Your eyes, the resolution is not as good as the. Right? So when you not see anything, actually there are some single particles that actually was there. That's more than enough. Yeah. Okay. So this is one trick that you can use. Don't sprinkle, like a lot of powder. We just need a 1 or 2 particle stick. We found it. Hallelujah, very nice, right? Very good picture, right? We can disperse the samples, right? I think we can use ultrasonic bath, we can use some, other methods, and we can use some cleaning method as well, right? Plasma cleaners, iron polisher, and so on. So don't put too much liquid, and make sure it's dry because all the water vapor will introduce some gas particle inside the chamber, and it's always moving. Normally, I will just use a hot plate, just put my sample on top of a hot plate just to make sure all the water gone, right? And of course, we can have a plasma cleaner or hand polisher if you want, but that could be a standalone thing. Before I move on to my earlier presentation, just for this masterclass, I have curated 8 different samples, and all these 8 different samples will have different characteristics to show. Okay, so you will see something like this. Aluminum, 1 particle, right? If you sprinkle the thing, you won't see anything. You put the carbon tape, you cannot see anything. So when you use the method, you will have 1 single particle. And from here to here, the ridges is only about 3 nanometers. It's very, very small particle. This is the materials they use for just now when to see the ion beam. This is the materials, YAG, right? Some alloy for battery research, the NCM, LFP for the battery research. Anybody doing battery research here? Yeah. Oh, okay. Electrochemistry battery. Yeah. agricultural materials, palm fiber. But of course, we don't have this FEP here in this, right? We don't have a FEP here. But if you have FEP method or you want to use some biological sample, look for topographical in backscatter detectors. You won't get, because backscattered is the electron that hard hit your sample, so it gives you materials contrast information, right? It will tell you which one is high voltage and so on. High molecular mass and so on, right? But topography, we want to see the surface. You see, so you use the wrong electron, you won't be able to see what you need to see, right? So it's important for us to know what kind of electron, what kind of formation we need. So when electron hit the sample, there are a couple of things will come out. Secondary electron, backscattered electron, SE2. SE2 is a low energy, and we have X-ray. Okay, so all these will come out from the samples. Alright, so it's important for us to know which one is which, and normally, rule of thumb, secondary electron is low energy. Low energy. Why I keep saying this? Because we have a special detectors on top. We call it ESB. It's called energy selective detectors. Do we have ES? We should have, right? ESB here. Should be, yeah, right. So this detector is very good because you remember when I said the electron can accelerate back to the columns? When the electron go, it contains a secondary electron and backscatter. But we have energy filter. It's a negative plate, right? It will repel away the low energy ones. So what you see is really a real DSE information, backscatter electron. I will show you the detector later, right? So we have all these techniques to really capture what you want to know, what you need to know.
So you have one detector only which will act both as BSE detector as well as kind of through the lens detector?
We have different kinds of detectors. There are some only SE detectors, some are BSE, and this ESB is called energy selective backscatter detectors. We can control the repel voltage. So if we want more topographical, we can make it 0, right? So all electron coming. But if you want to repel all the things, we can just set it high, then only backscatter will be, right?
In the AC1 kind of secondary electron, the energy range is still between 0 to 50 eV, right?
Yes. Yeah, I have this diagram. So this is just to give it, the green color one is a secondary electron, right? So low energy, right? Low energy, but it's in the surface, right? They give you information on the topography, right? You want to see the high or low, right? Are you getting bored or are you still awake? When I give lecture, I always need to ask this kind of question so that
You don't want to cut their marks, right?
Huh?
The sleep.
Yeah. No, I will set the difficult exam question. Yeah. So when you see topographical, you can sense that some are higher, some are lower, right? That image you cannot see, right? These are actually the same image, but that one they give you the sense that probably this one is the high molecular mass, this is low molecular mass, right? They give you different feeling of the sample.
Yeah.
Yeah.
So that
Sorry.
was image using the backscatter.
Backscatter, secondary. Okay. For those who working with very charging samples, polymers, biomaterials, remember, SE detector is your best friend. That's the best detector for you. Don't bother to go backscatter. You won't see anything. SE detectors. Okay? Take note of that for those polymer people. Okay, all these are, I mean, you can go Wikipedia and learn how the signal when it hit the filling scintillator, photomultiplier is just, but this is the physics that, you just know that this detector exists, it can give you the information, right? We call this detector SE2 detectors, or some people they call it FR on. Sorry, yeah.
Can you go back to the
Sorry, yeah,
slide?
yeah.
So that AC2 detector, is that the, if you have an inland detector?
Yes.
The,
Inland is actually on the column.
color.
Yeah, why we put there? Because we use the beam booster. You see, you remember when decelerate and we accelerate the other way, we want all the electrons to go there. But this SE is normally on the chamber, in the chamber.
So if I image with the inland detector and this AC2 detector that will go to the
Yeah.
So what do I imagine?
So-
I'll see the difference in the image.
Okay, this one SE, it will give you the low energy. the surface information. So if you want topographical, you have a charging sample, this is your best detector. In lens is on the column, right? It's accelerated. So you will see more backscattered kind of information. But of course, our inlens can do both. We later can see in the afternoon how our
higher resolution.
higher resolution. Yeah. So it's really depend on what we want. We even can have a detector below because it's STEM, right? So you don't have to buy TEM, right?
So actually, the students should juggle with both the detectors and see which will give the better effect. Right?
Yes. My favorite detectors is actually ESB, Energy Selective Backscatter Detector, because that detector would give you the SE together with BSE or only BSE.
So there is a lot of difference in the hardware, or it's just the positioning, or
Yeah, just the positioning of the detector. And most of our detector actually you don't have to put in, put out, and so on, right?
Oh.
But of course we have those backscatter detector that we need to put in below the. I will show you. Okay. I have so many to share, but I only have 1.5 hours. Inlens, this is what ma'am mentioned. So this positioning is inside the column, right? So it will capture most of the electrons, I will say, most of the electrons. But the problem is sometimes the inlens is that you cannot differentiate between secondary or backscatter. But if you just a nice picture for your publication, this is probably one of the better detector that we have, right? And do you realize that actually our column was widely copied by our competitors? I will not mention which company, but if you ask me, I will tell you. I will prove to you that they are copying our design, 100%. Even there's one company from mainland China. They openly, this is not recorded, right? Okay, so you can see that certain particles appear brighter than the others. Right. So if, for example, you are working on catalyst, then you want to make sure, oh, my catalyst is evenly distributed. How do you prove it? Backscatter, right? So when you can see your platinum, around us very uniformly, then. But if your sample is all platinum go to one side and the other not have platinum, then you cannot say your catalyst is evenly distributed, right? So these are one of the proof that we can use. Move forward for the working distance, optimum, too small, tilted sample, and too large, right? So just nice, because the OES detector is just below the length, so certain working distance is good. Rule of thumb, 2 to 3 nanometers. Okay, I know some facility they are very nervous when the students start to go in very near, but actually I would say 1 is still okay. But I know some they put the rule no lower than 4 nanometers. 4 millimeters, right? So give and take, right? Too small, the interaction will not be a lot, right? Because you only have this particular at the center. Too large, wasted electron, right? Tilted the same. So there is always you need to understand this physics on your head when you move the things around.
What is the maximum tilt we can go for in this configuration?
90? Yeah, for Ebsd is 70. Yeah. But I mean, nobody really did that to me.
that much. Now I don't know.
Our BSC detector, later we'll show in the afternoon that we can control the gain and the signals, the processing, and even we have a multi-segment. We can choose that I want this segment and this segment. I don't want different settings we can do. Right? This is my favorite detectors. Located at the column, right? And this one we can control. So when we apply some filtering grid, the secondary electron will be repelled. Okay, the backscatter will go in. So this is what we call a true BSE image. So a lot of people they say, oh, I'm BSE detectors, but your BSE detector cannot filter out secondary electron. So you want materials contrast, but you still see some topography, right? This one you can totally tap off. Right? Image. So grid is 0. Correct me if I'm wrong, but you can see here, you can still sense that something higher, something lower. Yes, you can sense the top, but you go to the 500, you cannot see. It's flat. It's the same sample with different filtering. Yeah, you can sense.
You want to just filter the secondary electrodes, right?
Oh, wait.
Read this 7, 500, 300.
Please come back.
Yeah, sorry. Yeah.
Isn't that an overkill? Maybe 100. 100 might be okay.
No, 50 volt is the one that coming out from the sample. But you remember it was accelerated, right? So slightly higher energy actually. So we want, yeah. So we
100, I think fine. 500 to go 500. You know, we lose a bit.
but you totally cut off the back
Yeah.
secondary. Yeah. I mean, this parameter you can play around. You know, you want to know what's the difference between 100 and 1 volt and 102 volt. You can do it, but you know, you want. Sometimes we just like low, high, that's it. You know. Same sample, different feeling, right?
Every other parameter is
Yeah, this is exactly same sample, but by controlling, let's say this one is just a voltage, we use a different voltage, it could have inversion of matrix contrast. So the duct become brighter, become dark. Okay, when you do the secondary electron imaging, be careful of this. So your sample might not be flat. So I simply draw there's a valley and there's a mountain. Right? So what does it do? Ideally, this kind of things, you can see the whole plane, very simple, right? But when your sample hit the valley or hit the mountain, it will happen to have this, you know, the pointed always very bright, and this is very dark. You can see. So it's because of electron accumulated at the mountain, right?
what kind of sample was that? It's very nice facet.
I can't remember what it
It's
is.
aluminum. Right? You see.
So we have a shadowing effect, and we have a So this side of the things, if you look at that detector, you won't be able to see because it's blocked. Right? So sometimes it appears very dark. It doesn't mean that information was not there, but just you cannot see. So nowadays the EDX detector normally we use a two side, the EDX, right? So we want to see both sides of the thing. So I know some of our clients they are very crazy about it. I have a lot of money. Please put more detectors so that they maximize out of our 14. Yeah, they just crazy. I want add this, please. You know, our sales people will be very happy. But you know, what kind of information you want, right? So what I'm trying to say is that when you have your sample, keep it flat as possible. And when you say flat, it's not flat by your eyes, it's actually flat by the electron microscopy standards. It will give you a better image. Unless, of course, you're talking about particles. That's the way you get it. STEM detectors, we have STEM detectors that are actually placed below. So the requirement is, of course, your sample must be thin enough that allow the electron to pass. And of course, we cannot beat the transmission electron microscope because transmission electron microscope EM, they use a 200 kilovolt. Our maximum 30 kilovolt. So you won't be able to penetrate that details, right? So don't use our SEM and try, I want to get a diffraction pattern of it. No way you can get it, but you can get the sense of it.
How thin the sample should be?
10 nanometers. Yeah. 10 nanometers.
So this is
Yeah. 100 is okay. 20 I think is the optimum, but 100 is fine. I mean, there's no much difference between 20 and 100 to be very honest in the in the.
So this is the same TM sample what we put, right? Now.
Yes.
The TM station.
Why we need this? The good thing is this. For example, you have a sample, big sample. You want to chunk it, right? You want to make it a thin layers, right? So what happens is that if you have TM on spot, you cut it very hard with the iron beam and all that. You cut with laser. You took it out and you put in the TM. And in TM, you need to do the 20 calibration. You know, if you use TM before, you know what I'm trying to say. There's 20 calibration you do, then you need to find your sample. What if the sample lost in between? The moment you took, gone. You know, you just spend 2 hours just to cut the samples, then it's gone. With this detector, actually we don't have to take out. The sample is still there in the chamber. You just put in the detectors and you can see immediately. It's much faster. Much faster.
So we needed to place it in a special like sample holder.
Yeah. Yeah.
This is the sample holder.
This is the one.
Right.
How much?
12 samples.
Very cheap, right?
The cost?
We have the
Yes,
stem
yes,
mode, right?
yes,
We
yes,
have-
yes. This holder we have. The detector also.
Yeah. We have a lot of time of sample holder. We can do it a lot of time.
So the sample preparation is also done on FIB.
Yeah, the sample preparation for the TEM and sample preparation for these detectors are identical. So the use of it actually, the utilization of it, instead of going to the TEM directly, you can put your sample here, have a primary investigation of your sample. That is point number 1. Point number 2 is that for biological samples where 200 kV is too much, you can put your sample here and can analyze under 30 kV accelerating voltage. So that is the use of it actually. I mean, yes, certainly the FIB with a 10 lambda preparation kit with the stem detector can be the ideal thing to do. But here in FESEM, you can externally prepare your samples, maybe powder samples in a colloidal solutions with alkylation and all those things. You can put your sample in the grid and put the grid here for the initial investigation.
Just the regular TEM grid.
Yes, regular TEM grid,
Yeah.
3.05 mm. So that is the dia of that particular.
Without taking off. I always very scared of handling the TL.
Yes, yes.
Oh, one mistake. My professor used to say that your hand is too big to do all this small thing, you know. You will lose it. When you lose it, actually we spend a lot of time just to cut the thing down, right?
Example.
Yes.
So
Yes.
it's the-
So again, I won't go into detail because this is a course on its own. What is the dark field mode? We can discuss later if you are interested. I just give you the. Okay, this is just an illustration how it forms. Yeah. So it's the same sample, but just by choosing which part of the detector we activate, it will appear differently. Okay, material scientists they like to see the same thing in different lights, right? So we can see. I have a couple more examples later on if required. Right? We even can do the half group on the machine and another group we can discuss things.
Yeah, that's what.
Yeah. Yeah. Okay, so I'm going to go through very fast on here, different pictures, different things that's most of it I personally took on the machine, and I hope it will inspire you to when you review a paper publication,